A second type of distribution that we can work with is called the Poisson distribution. It's named after a mathematician named Poisson. But the question that the Poisson distribution attempts to ask is very similar to the binomial. The binomial wanted to know the probability of x successes in n trials. Poisson also wants to know what is the probability of x successes. But instead of in a certain number of trials, it wants to know in a certain amount of time. In other words, we'll say some event happens on average 3 times an hour. What's the probability this hour it's going to happen 5 times? And to answer that question, we use the Poisson distribution. And some characteristics of the Poisson distribution is that we are interested in some number of successes in a fixed interval. Usually those intervals are a certain amount of time, a day, a week, a month, a year. But it can be any fixed interval, like an editor might be interested in the number of errors an author makes per page. And so a page is the fixed interval that functions as the time interval. But usually we're talking in the context of time. And we also need to know, or we will have, the average number of successes in that interval. So the editor knows that an author makes, on average, 3 errors per page. The distribution itself, we will notate the distribution very similarly to how we did the binomial. We'll use the x to say that's our random variable, the tilde to tell us it's distributed. But this time, because it's a Poisson distribution, we'll use p to represent Poisson. And the only variable we need for the Poisson distribution is the mean, or the average number of successes in the interval. As you might expect, the expected value is the mean that's given to us. That's no surprise. But the standard deviation turns out to just be the square root of that average. And so these formulas can help us shortcut that process as we attempt to actually use the Poisson distribution. And just like we did with the binomial distribution, when we're using the Poisson distribution, we will actually have the calculator find the probabilities for us. We just need to know how to use the calculator to get the information we want. Very similar to the binomial, we'll hit the second button. And then you're going to hit the vars button, because above the vars, we remember it says distribution. And then we need to select the correct distribution, as there are several in the calculator. Again, near the bottom are going to be the 2 we'll use. One is called Poisson PDF. And just like the binomial, that gives us the probability of exactly x successes. And then the other one is the Poisson CDF, opening a parentheses. That's the one that gives us the probability of up to and including x successes. And again, similar to the binomial, the format we will use, if you don't have the prompts on your calculator, will be the Poisson, either C or P, they both work the same, df. And then the first number you'll enter in is actually the average, or the mean, over that time interval. The second number is the x value that you're interested in finding. So let's see if we can use the Poisson distribution in an example. Let's say a certain hospital baby unit has an average of 4 births per week. And we're going to randomly choose a week. A week is randomly chosen. First things first, let's describe the distribution. The distribution is a Poisson because we're talking about a time period, an interval, a span of time, 1 week. And in that 1 week, there is an average of 4 births in that week. That is the distribution. Now we can find the expected value and standard deviation of the number of births the hospital has per week. Well, the expected value, that's just mu, or the average, which is given to us. The expected value is 4. The standard deviation, or sigma, is the square root of the average. And the square root of 4 is 2. So average of 4 births with a standard deviation of 2 births is what we would expect to happen on any given week in the baby unit of the hospital. So let's find some probabilities and see how likely various things are to occur. I'm always interested in how often the average occurs. So what is the probability exactly 4 babies are born this week? What we're asking is, what is the probability that our random variable x is exactly equal to 4? Now, because I want my probability to be exactly equal to 4, what I'm interested in finding is the PDF for the Poisson exactly equal to 4 in that time interval. So we will do the Poisson PDF, probability distribution function. The first number is the average of 4. The second number says we want exactly 4 to occur. So let's see what the calculator says when we pull it up. Very similar to the binomial, we'll hit second and distributions. Scroll down to the bottom, and below the binomial, you'll see the Poisson distributions. The Poisson's PDF. And the calculator, if it gives you props, will ask for lambda. That's the Greek letter lambda is the average. So for lambda, the average we say is 4. The x value we're interested in is 4. And when we paste, you'll see it puts it in the calculator for me. If you don't have the prompts, again, you can just type in 4, 4 and close the parentheses. The comma's above the 7. And we see the probability that we get exactly 4. Even though that's the average, the probability that actually occurs is only about 19.5%, 0.1954 when we round. So that might beg the question, what is the probability of fewer than 4 births this week? The average of 4 only has a less than 20% probability. What's the probability that x is fewer or smaller than 4? Well, the calculator can only do exactly equal to a number and down. So first, let's identify that we're really looking for the probability that x is less than or equal to, not 4, because 4 is not included, but less than or equal to 3. Because we want to be less than or equal to 3, counting all the possibilities up to 3, 0 plus 1 plus 2 plus 3, that's going to be our CDF, or our cumulative distribution that adds up all the values up to that point. The Poisson CDF, which has an average of 4, but we want to know up to the number 3. So we go to our calculator and hit second distribution. Down to the bottom, you see Poisson CDF. The mean is 4. We want to go up to 3. And when we paste, types the numbers in, or you can type them in manually if you don't have the prompts. The probability that we get less than 4 is 0.4335. So there's a 43% chance we're actually less than the average number of births. Let's say the hospital can only handle about 1 baby a day, 1 birth a day. It's a small hospital, a small baby unit. So we want to know what is the probability seven or more births occur this week. What is the probability that x is greater than or equal to, because it includes 7, it said 7 or more, births this week? Now, the thing about the Poisson distribution is there's not actually any maximum. In theory, there could be 1,000 births this week at this hospital. It could go up that high. Now, if the average is 4, the probability is basically 0, but it could potentially happen. So when we're doing greater than 7, this is actually impossible to calculate straightforward, because we'd have to do 7 plus 8 plus 9 plus 10 plus 11, and we'd have to go all the way to infinity. We can't do that. So just like we did with the binomial, when we want greater than, we're going to actually work with the complement. We're going to do 1 minus the probability that x is less than or equal to the opposite set of numbers. Now, if we're going from 7 up, this time it includes the number 7. So when we count down, we don't want to include 7. So we're going to start at 6, counting down. So in the calculator, we'll type in 1 minus the Poisson CDF, cumulative. It's going to add those all up. The average is 4. And we want to go up to 6. And then we'll subtract all of that off of 1 to get the complement. So we'll type in 1 minus second distribution up to Poisson CDF. The average is still 4, but this time we're going up to 6. And when I paste it in, and we do 1 minus that value, we get a probability of 0.1107. 0.1107. And so if they're not ready for 7 or more births this week, that's going to happen 11% of the time. They might need to expand their baby unit in the hospital. So that's the Poisson distribution. Very, very similar to the binomial. The difference is now we're talking about the number of successes in a fixed interval, usually a time interval. So take a look at the homework assignment to practice a few of these, and then when you come to class, we'll continue working with Poisson and that distribution.